Hello. In our previous video, we defined Newton's law of gravitation and stated that that's the law that we base gravimetric surveys in geophysics on. In this video, we'll take a look at another useful concept in gravitational theory, which is the gravitational potential, we'll call it U, and also we'll define the concept of gravity effect. So in our previous video, we saw that Newton's law of gravitation states that the force of gravity between two objects is equal to negative g times, I'm going to put capital M here for the first mass and lowercase m for a second mass, divided by r squared, where r is the vector between the two objects, times r hat, where r here points from big M to small m. So let me just draw a picture of that. Let's say we have big M here at the origin, the first mass, and we have small m over here at some other point. I'll call this one small m. So r here is the vector that points from big M to small m. R hat is the unit vector in that direction. I'll call this one r, and the unit vector in the same direction, r hat. And based on this law here, F points back in the opposite direction here. I'll call this F. Now, let's say that we want to define the gravitational field around big M for an arbitrary mass, m. To do that, we found the concept of the gravitational acceleration, g, useful. G is just equal to F over small m. And this is a constant, so it's this value, g, is independent of the small mass here. Okay, so that's sufficient to define g, and we can say that this vector here instead represents g. That's going to be a more useful concept for us. So we'll call that vector g, and it points back towards the origin where big M is located. Now, this g field, the gravitational field, represents a flux variable. Now, if you take a look back to our video on the Poisson equation, you'll know that the flux variable is just a vector field, and the g field is what's called a conservative field. So this is going to rely on your understanding of the vector operator from a previous video, and also on the Poisson equation. We won't get to the Poisson equation in this sequence, but understanding what's going on in that video will help you to understand this one. So because g is a conservative field, we can actually define it from the gradient of a potential field. So we're going to define what is this u here. So g is the field given by the negative of the gradient of some potential field u. So we will allow g to be defined in that way. Now we want to calculate what is u as a function of this distance r from the origin. So we'd like to calculate what is the gravitational potential u as a function of the distance r. So here, this r is equal to the magnitude of the r vector, so the distance from the origin, the distance from this mass right here. So based on this definition, u is we have this gradient, and that gives us g. We can say that u is the integral from any arbitrary point A to the point of interest R of the gradient of U along some path. So this is a path vector, so it goes along a specific path. Let me draw the meaning of that. So let's say I start from some arbitrary point over here. That one is a distance A from the origin. So A here is the magnitude of the A vector. If I start from that point and travel along any path to get to my point of interest R, and this dr is an infinitesimal piece of that path, when I arrive at this point, I'll have my value of U. And the nice thing about conservative fields is that its value is actually independent of the path that we take. So that's an important concept. We are going from some point A to this point right here, and it doesn't matter what path we take, we'll get the same value for the potential. So using this equality right here, we can say actually that U is the negative of the integral from some arbitrary point that we select, A, to some point R of the G field dotted with whatever path we choose to take. Okay, so that sort of sets up our definition for the gravitational potential. In the next video, we'll evaluate this integral and actually work out what is U from our definition of G.